Welcome back to Computer Science 4300. Today we are doing lecture number 12, which is ray casting and line intersection. This will be used in assignment 4 and in your project. So before we get started on diving into what ray casting and line intersection are, let's look at our use case for it. So this is the solution code for assignment 4. So I'm just going to run this real quick. And we have a game called Definitely Not Zelda for legal purposes, right? So in this game, I'm controlling something that happens to look like a popular NES character. And I think there's desktop audio here. So let me just turn that on. Let me see. You can probably hear that. I'm not sure. But anyway, so there's different types of NPCs in assignment 4. Some of them have sort of set paths that they follow, and some of them, like this knight over here, when I cross into line of sight of that knight, it's going to chase after me, okay? And if I go back, then he's no longer in line of sight, so he'll go back to his starting position. So just again, if I move up and he can see me, he's going to come after me. If I move down somewhere that he can't see me, he's going to go back to his starting location. Also, if I go up here, these have the same behavior, so as soon as they can see me, they'll chase after me, and as soon as they can't, they'll go back to their starting location. So to accomplish this, we're going to use ray casting. And ray casting, essentially, is just drawing lines and seeing if they intersect with other things. So here, we've got some tiles in the map that block vision. And so as long as these lines from the center of my character to the center of the NPCs intersect with a vision blocking line, oh look, there's someone coming to get me, then they're not going to be moving. But as you can see, as soon as this line is no longer broken, that NPC is going to come after me, right? And as soon as it becomes broken, it's going to try and go back to its home. So that's what we're trying to accomplish in this lecture, is to know the mathematics that lets something like this be possible, and ideally for it to be pretty quick as well. So let's jump right into the slides for this lecture. So lecture 12, 2D ray casting and line segment intersection. So what is ray casting? Ray casting is the name for a technique which has many, many, many applications in games. We just saw one of the very basic ones. So ray tracing, have you ever heard of ray tracing before? It's kind of becoming all the rage now that we have like RTX graphics cards. Like you can have RTX mode on in Minecraft and it's ray traced, which is pretty cool. I didn't think I'd see that in my lifetime, as like actual ray traced in real-time games. So ray tracing, if you've ever heard of that, is just a lot of ray casting, okay? So intuitively, if we're thinking about in 3 dimensions, because that's the world that we exist in, we cast rays outward from my eye to the world. What do they hit, right? So it's very, very heavy on vector math, but has many, many useful applications. So for example here, you can think of ray casting in 3 dimensions almost like a camera or your eyes, right? So when a camera takes a picture, let me turn on my laser pointer over here. When this camera takes a picture, there's going to be some things out there in the real world that have physical properties. There's also ideally going to be some light source, okay? So what happens in the real world is that you have some image plane that's formed by your camera, right? Your camera lens can see a certain viewport up and down, side to side. And so light in the real world is going to bounce off your objects, and if that light happens to bounce back into the camera lens, then that's something that your camera can see. And so that's essentially what's happening. It can be much, much more complicated than this simple example where, you have multiple mirrors and all sorts of crazy stuff. But essentially, it's just a bunch of rays of light, usually it's light, but rays of something that are intersecting, bouncing off of objects, and then ending up somewhere else. So ray casting, the basic operation that we're doing is we're drawing a line between 2 points in space. And we're going to detect if a collision occurs at any point with that line, and where that collision occurs as well. So ray tracing essentially is like, where did that thing bounce to? Or where did it stop? Where did the light stop? Where did the shadow begin? That sort of thing. So if no collision occurs on a line between 2 points, then effectively they can see each other, right? This is called line of sight in a lot of video games. So, if you're shooting with a hit scan weapon in like Counter-Strike Go, where you can see is what you can hit. And you can think of a bullet coming out of an op or an AK or something like that, a bullet, a projectile coming out as a ray that we're casting. And in fact, ray casting is how you do collision detection for hit scan weapons, because it has no travel time, so you instantly need to know if there's a line of sight between 2 places. So bullets, there's one example of why ray casting is important. Line of sight for our NPCs seeing us is another one. Lighting effects have to do with ray casting. So there's lots of really interesting things that we can do with ray casting. 2D ray casting primarily solves problems that deal with light and visibility, or like hit scan weapons. But hit scan weapons are essentially visibility as well. So, for example here, you can see... Should I open this example? Now, we'll have another example later. But essentially, we're going to have a light source in a game, and that light source is going to be casting out these rays. And whatever it intersects with is going to be visible, and whatever is behind that intersection is not going to be visible. And you can get really fancy with this and have multiple light sources where you can cast shadows and have different lighting intensities, but the basic mathematics of it all is the same. It's calculating where the light hits and where the light doesn't hit. So you can go, here's a website that you can go to. It has a really nice little interactive tutorial with this, but I'm not going to go there. You can go play around with that if you want. And this is a game called Third Eye Crime, which deals a lot with this sort of ray casting. So in this game, here you have the player character in the middle, and you have these NPC guards or thugs or mafia or whatever they are, and they're trying to detect intruders, right? So you can see that these NPCs have a vision radius or a vision cone in front of them, and they can see whatever's in blue. So these characters are walking around, they can see what's in blue, and you're trying to sneak past them to either steal the treasure or make it to the exit or whatever. So that's one really cool application that, by the end of this lecture, you will be able to implement something like this, which is really cool. Here is something that I did up in SFML and C++. And again, this is what you'll be able to do at the end of this lecture. And it's just a really simple example of drawing some things one color if the light can see them, and drawing them another color if the light can't see them. And this tricks our brain into thinking, oh wow, this is an actual light source where you can see some things if it's lit up, or it's shadow behind it, when in actual fact it's just triangles of different colors. All right, so the very, very basics of ray tracing asks the question, is anything blocking the path between these 2D points? Now, if we were in a 3D game, it would be 3 dimensions, but we're not going with the extra complexity here. We just have a 2D game engine that we're implementing. So how would we detect this mathematically? All right. So mathematically, the path between 2 points is blocked if the line segment between the 2 points intersects with another existing line segment. Okay, so essentially, if we draw a line segment, so a line has infinite length, a line segment has finite length. So we define a line segment by its 2 endpoints. So we're asking, does the line segment between the 2 points that we're concerned with, so that might be the tip of my gun and your forehead in a video game, or it might be like a light bulb and an object that you want to be illuminated, whatever that is. You draw a line segment between them, and if that intersects with some geometry that could block it, another line segment in this case, then there's a problem, right? You're going to have to detect that. If you were doing this in 3 dimensions, the line segment here would actually be a plane. So you'd be concerned with, does this straight line in 3 dimensions intersect with a plane in 3 dimensions? But again, we're only doing 2D for this course. So in this case, you would have a block path, and you'd be able to detect, okay, once I've implemented the mathematics to detect these 2 line segments intersecting, I know that the path is blocked between P1 and P2. And depending on the application, we may also want to know where the first intersection is, right? Because here we just kind of wanted to know, okay, maybe do we see this? Does the bullet hit it, right? But in another application, we may want to know where the first intersection occurred, right? So not only did the bullet travel from P1 to P2, but where was the intersection? Because I want to draw that little dot on the wall or something like that where the bullet hit, right? Or I want to illuminate the thing that should be light and the things behind it should be dark. So not only do we want to know if any collisions occurred, but where the first collision occurred. So how are we going to do that? So far in this course, we've been using the vec2 class to represent points in 2D, right, as a 2D vector with x and y components. So if we're talking about line segments now, a line segment can be defined by the start and end points of a line using vec2. So what do I mean by that? Well, if we have one vec2 here called A, which has an x and a y component, and another point here, or a vec2, with an x and a y. So this is A, this is B. We call this line segment AB. Pretty intuitive. So if we have points A and points B stored as vec2 in our engine, then line segment AB is just the line segment between them. So let's do some vector subtraction, and we've already done this before. So R is going to equal the line segment, essentially. So we have point A and point B. If we subtract, so if we take destination minus origin, remember from our previous lecture, we get the vector pointing from the origin to the destination. So B equals A plus R, and R is this vector or line segment between them. So we take point B, we take point A, B minus A, that equals R. All right, so we've seen this before. But let's do something interesting here. Let's scale R by a scalar value, meaning just a floating point number. So if I don't scale R by anything, this line segment AB is just equal to 1 times R, right? Where R is B minus A. But what if I said 0.5 times R? Okay, well, that means it's 0.5, so it's half the x distance and half the y distance. So 0.5 times R defines the line segment, which is halfway between A and B. Or sorry, it goes from A to halfway between A and B. What about 1.3 times R, right? So this would take the line segment and extend it past B a little bit. So what we're going to do is we're going to scale R by a scalar value called T. So I know this is a lot of, you got A, B, T, and R, but just try and review this a bit later. So T is the scalar value that we're scaling R by. So here in this example that we showed, T is equal to 0.5. And if we've got just line segment AB, then that's when T is equal to 1. Okay. Now you can also scale a line segment or a vector by a negative value. And if you scaled, for example, if you took this and you scaled it by negative 0.5, you would actually get something like this, right? Because you negative the x, you negative the y, essentially you're just heading in the opposite direction. But we don't need to worry about that case for right now. So line segments, let's add another line, okay? So we've got points C and point D. So we got C here and D there. And so S is going to be D minus C. So we take the destination, we subtract the origin, and we get the vector between them, which is our line segment. Now, before we scaled R by T, now we're going to scale U by S. Okay? And just look at this. When R and S have the correct lengths, the line segments are going to be pointing to the same place, or they're going to intersect. So what we have to do is find the correct scale values for R and S that make them meet. So in this example, I've crafted it so that if you had T equal to 0.5 and U equals 0.5, then A plus 0.5 times R would be equal to C plus 0.5 times S. Okay, so what we've done there is we've found where they intersect. And it turns out that the calculation of where they intersect is also needed for if they intersect. Okay, so they're going to intersect, and this is the point at which they intersect. So here we have B, right? So B is equal to A plus T times R, and D is equal to C plus U times S. And we know the lines intersect where B and D would be equal. So what we're going to do in order to get the correct scalar values is, if these are equal at some point, then we'll just set their equations to be equal. So where B would equal D, right? So just look back. Right here, we essentially have B equal D at this point with these scalar values. So we set both of these equations, we take them and we set them equal to each other. And the lines intersect if both T and U are between 0 and 1. Now, why is that? Well, if we had a T value greater than 1, then our point would be out here somewhere. If it was less than 0, it would be out here somewhere. So if we're intersecting out here, or if we're intersecting up here, right, then this is not an intersection between the 2 points. So just keep in mind that T and U both have to be between 0 and 1 to make sure that that intersection is actually in the middle of this whole structure. So let's take that equation again, but now you're looking for that, and how do we solve for two unknowns? We have two equations and two unknowns. How do we do that? Can we solve that? Anyone out in the chat have any idea? Remember, because normally, if we have n equations and n unknowns, we can't solve that system, right? But, okay, spoiler alert, we can solve this system, and the 2D cross product is going to come to the rescue. What in the hell is a 2D cross product? All right. Well, first, let's think about what the 3D cross product is. So, a cross product in 3D space, so say we have this vector down here, vector A, and we have another vector, vector B. Two vectors in three-dimensional space define a plane. Okay, so you see this is a plane down here. The cross product, A cross B, produces a three-dimensional vector which is orthogonal to both A and B. So it's pointing straight up. So it's the normal vector. So the cross product gives you the normal vector to a surface if you have the equations of two vectors, all right? However, in 2 dimensions, the cross product doesn't make a lot of sense, right? Because we can't have something normal to something in 2 dimensions because it would be pointing upwards out of the 3rd dimension. I don't know. But it doesn't make as intuitive geometric sense in 2 dimensions. However, it does give us a really interesting property, and we will use that property to help us solve these equations. So the 2D cross product is defined as such. So A cross B is going to be equal to the x component of A times the y component of B, right here. So we take the x component of A multiplied by the y component of B, and we subtract the y component of A times the x component of B. And that's going to give us a scalar value, okay? So scalar, again, meaning just one floating point number, one real number. That produces a scalar. But if we look here, there are two interesting properties of the 2D cross product. The first interesting property is that A cross A is equal to 0. Well, why does that work? Well, if we think up here, let's look at a situation where we have A cross A. Well, that would be A's x times A's y, so x times y, minus A's y times A's x. So if we're crossing something with itself, this term is going to be equal to this term, and we're subtracting them, so it's going to be 0. Okay, so that's a really simple proof. We also have this property, which is if we have A plus R cross S, then we can do the sort of foiling of that. Well, it's not full foil, but we take the multiplication, we apply it to the first one, and then we apply it to the second one, just like normal multiplication. So A plus R cross S is equal to A cross S plus R cross S. So those are the two properties that we're going to use in this derivation. So now that we have this, let's choose one of our t or u, and we'll solve for it, and then we'll do the other one. So let's solve for t. Oops, I went back a slide. So here we have our equation. That's the equation that we started with. Now let's apply the cross product of s to both sides. So here's what we get with that. We take the left-hand side and we cross it with s, and we take the right-hand side and we cross it with s. Now we have something plus something cross something, so we're going to expand that using this formula right here. So let's see what we get when we expand that. Well, we're going to get A cross S plus T times R cross S, okay? And on the right-hand side, we get C cross S plus U times S cross S. But what did we say before? S cross itself is going to be equal to 0. And this is the only U over here. And so now we have a system with just one unknown. Okay, so we've eliminated the U variable from there. So now we have, we just move, what do we do here? Yeah, we subtract this from both sides, so A cross S. So we have T times R cross S is equal to C cross S minus A cross S. And this right-hand side right here is we have two things cross S, so we can just bring that outside. So now we have C minus A cross S. So if we're interested in T, we just divide both sides by this value, right? So we're going to divide that by this, and we get T is equal to C minus A cross S, all divided by R cross S. And that's just a couple of multiplications and subtractions, and we're done. Let's do the exact same thing. However, now we're going to solve for U. So I won't take as much time on this one because it's the exact same thing in reverse. There's our original equation. This time, instead of cross-producting by S, we're going to do it with R. So we get the cross product here. We expand it. We've got our 0 term in R cross R, which eliminates the T. And then we just move things to the correct side. And we divide by S cross R. So we have U is equal to A minus C cross R divided by S cross R. All right, so now we have T and U. So T is equal to this, and U is equal to this. So all we have to do is plug it in. However, there's a little optimization that we can do, which is really nice. Here's another property that I'm not going to prove, I'm just going to show you, is that R cross S is equal to negative S cross R. Okay, that's because there's a subtraction in between, so it gets moved outside when you flip them. So, look at this. We've got a C minus A here and an A minus C here. So, we're going to rearrange the above, and we're going to say U is equal to, initially, A minus C cross R divided by S cross R. However, we can invert this term, right, because it's negative, and we can flip the things that are crossed in the denominator. You see how that works? So because of this property, we can turn this line into this line. And what does that do for us? Well, this is a slightly optimized version because we have T equal to C minus A cross S divided by R cross S, and we have U equal to C minus A cross R divided by R cross S. So we have C minus A computed twice, and we have R cross S computed twice. This means we can just compute them once and store the values if we want to. So we're eliminating a lot of this computation. And so here are the two formulas that we end up with. And we have an intersection if both of the properties are true, that T is between 0 and 1 inclusive, and U is between 0 and 1 inclusive. Because we're only concerned with intersections that happen along the original line segment and not the extended line segments beyond 1 or before 0. And so all we have to do once we get T or once we get U is plug them back into the original equation, okay? So P is equal to A plus T times R, or if you found out U, P is equal to C plus U times S, P being the intersection point. All right. So that was sort of, the mathematical version of this. And here is the actual code that you're going to implement in assignment 4. And I've basically given it for you. So what we're going to do is we're going to have as a return value for this function, there's actually going to be two things that we want to know. The first thing is, was there an intersection? And the second thing is, where is the intersection? So instead of just returning a Boolean or instead of just returning a position, we're going to return both of those things. So I've got a little struct here, and inside that struct there's going to be a result and there's going to be a position. The result is going to be true if there is an intersection, false if there is not an intersection. Pause is going to be 0 if there's no intersection, and it's going to be the calculated intersection position if there was an intersection. So let's make this function line intersect. So that's going to take in 4 vec2 values, going to take in A, B, C, and D. Okay, so that's the endpoints AB and the endpoints CD, and it's going to return this intersect structure. And we're just going to implement what we had on this slide. So we're going to have vec2r equals B minus A, S equals D minus C. And now that we have these operations defined on our vec2 class, this looks just like math, right? There's very little like code here that doesn't look just like linear algebra. Then we have r cross x, but I have a variable here which is rxs. Okay, so you can't have like a symbol in the variable name, so I've just got rxs is equal to r cross x, and there's no actual like cross symbol in C++. So you would either define a function which is cross on the vec2 class, or you would define multiplication to be the cross product, or however you wanted to do that. Then you have a variable c minus a, which is equal to c minus a. Then you have t is just equal to c minus a cross s divided by rxs. And u, similarly, is c minus a cross r divided by rxs. And then if t and u are both between 0 and 1 inclusive, you're going to return true and where the point intersects. If there's else, so meaning that t or u were not within 0 or 1, you're going to return false, and you're going to return a vector 0, 0, because there's no intersection point. All right. Now that we know how to do line segment intersection, how are we going to use it for visibility? How are we going to use it for lighting? How are we going to use it for anything like that? Well, essentially, if line segment AB does not collide with any vision blocking entities, B is visible to A. Done. So, in our game, what we could do is find all the line segments in the level geometry and do all of those line segment intersections, and if there are any intersections, then we can't see it. That's sort of the naive way of doing it. Now, I will preface this by saying the way we are doing complete line of sight calculations in our game is not like the globally optimal PhD thesis solution, okay? But it is good enough that it will run fast enough to be in our course and we can use it for our game. There are all sorts of data structures like quad trees and geometric hashing and stuff that we could do such that we wouldn't have to do every possible line segment intersection with each other. However, this is good enough for this course. So let's do it and then move on to something a little bit more exciting in the next lecture. And we also may want to know where this intersected, right? So we can draw that little bullet mark on the wall or something like that. So how would we do that in our game engine? Well, what if our entities are made of rectangles and they're not made of they're not just line segments, right? What about non-linear game objects? Well, easy. They're made up of line segments, right? So you just decompose everything into its line segments and then do this check with all of those. All right? Now, I'm not going to go into this course about how to do line segment intersection with like Bezier curves or anything like that. They all exist out there. Or true circle intersection. That's a little bit beyond the scope of what I want to teach in this course. However, I just want to show you that this is possible. And the mathematics is so simple that you can do millions of these calculations per second. Okay? So entities can see up to the closest intersection. Anything beyond that is outside of the vision range. So you would have your NPC over here at point A and the player over here at point B, and you draw a line between them. And then you'd figure out all the bounding box vision radiuses or vision bounding boxes for all the entities in the game, decompose them into their line segments, and then do this intersection. All right. What about 2D game lighting effects? Light travels outward in all directions. So remember this? How would I do something like this? Because this looks pretty cool. This would be a cool effect to have in your project or an assignment or something like that. Now, I'm not going to require that you have this on your assignment because that's a little bit too much work. However, there are several possible ways to do this, but I want to show you a really, really simple, really cool example that I saw online, and I'll link to that so you can go implement this if you'd like to. And some people did implement this for their projects in a previous version of this course. So this is a website called Sight and Light. I'll link this out there in the chat if you want to play along as I'm going. And this is a really excellent website that I'm really glad has stayed up for several years because I continue to use it because it's really great interaction. So here you can see the same sort of effect that I was just showing on the slide. However, it's got this cool like skeleton effect that we're not going to be doing in this course. You could do it if you wanted to, but we're just really concerned with the lighting calculations here. So how was this done? Because it's a really cool effect. Well, it turns out that you already have all of the tools necessary to do something like this. So let's have a look. So first of all, what they do is they set up this little environment, right? And so there's going to be a dot that's drawn at my mouse cursor. And you can go through and you can read all of this, but I'm just giving my own sort of narration. So here's a mouse cursor. And what we're going to do is they give mathematics. This is a little bit different than the code that we gave in the lecture slides. So when you go to do this for an assignment, please use the code that we have in the slides. It's a little bit more efficient than the code that's here. So now what they do is they extend a array in the direction of the mouse cursor from the middle of this canvas. So you can see here how this is always pointing here. And then they take that line segment and they do the intersection checks. And then they draw a little dot wherever that intersects. Okay? So you already know how you would do something like this because you know how to form a line segment from the middle to the mouse pointer because we went over all of that geometry and math in a previous lecture. And then now you know how to do the line segment intersection checks with all the polygons inside this environment, including the boundary. So the boundary of the environment is also a line segment. Next, what they do is, let's say we had a light bulb, right? Light shines out in infinite directions at once. Well, infinite if the world is continuous, right? A lot if the world is just discrete. So in order to simulate the shining of light in a bunch of directions, what they did was say, okay, let's have the light source be at the mouse pointer, and we're going to draw like 50 rays equally separated throughout the 360 degrees. And then for each of those rays, what we're going to do is we're just going to do the intersection where it intersects in the level geometry, right? So this shouldn't be too hard to comprehend because what we just had up here, it's the same thing except you're doing it in a loop for 50 of them. And instead of the mouse pointer being the direction that it's shining in, now it's the source of it all, okay? Next, what they do is they're going to form polygons out of that. But I want to show you how these polygons are formed. So let's go over here to the blackboard. Alrighty. So let's say that we want to do what they just did. So we're going to have on our blackboard here a starting point in the middle. Oh dear, why can't you see this? Oh, is it picking up the wrong? Sorry, it's picking up the wrong MS Paint. This is another thing I was showing someone. Don't save. All right, so now it's got the correct blackboard. Perfect. So we've got a midpoint, and we've got a bunch of rays like this. It's taking a surprising amount of time to do this. Cool. So we've got a bunch of rays, and they've intersected somewhere. So these rays, how do we get from those rays to the polygons that we see here, right? So we're going from this step to this step. How do we do that? Well, it's actually pretty simple. If you look, what we're going to do is we're going to take each of these rays and we're going to figure out the angle between the ray and the x-axis. So this angle right here, we'd have this angle right here, this angle right here, this angle right here, this one right here, this one right here, this one right here. Then what we do is we take all of the line segments and we sort them radially, meaning we sort the line segments based on the magnitude of this angle, okay? So what we would have is we would see, okay, this line segment, this is the first line segment because it has the lowest angle. This is the second one because it has the next lowest angle, then third, then fourth, then fifth, then sixth, then seventh. So that's the second step. We radially sort those things. Oh, here I am not even using the blackboard. There we go. Why have a scene if you don't use it, right? So then what we do is we are going to draw triangles. So the triangle we're going to draw is from the center point. Let me draw this in blue. The center point out to 1, then from 1 to 2, and then from 2 back to the center point. That's going to be our first triangle. Our second triangle is from the midpoint to 2, then to 3, then back to the center point. Okay? So what we end up with is something that looks like this. And you can do something called a triangle fan as well. So if you can do a triangle fan, then your work is already done for you. But here we have 1 to 2, 2 to 3, 3 to 4, and of course we're finishing these back to the middle, but it just takes a long time. 5 to 6, 6 to 7, and then when you get to the final one, you loop back around to the first one. And that's how you form the triangles that you would draw for your polygons. So now we can see that that's exactly what's happening here, okay? However, look at this. Look around this corner right here. Sometimes it's overlapping it a little bit. Sometimes it's not overlapping it a little bit. Why is that? See? It's got this like really jagged movement to it, which is something that probably isn't cool. And down here, we can see that like part of this is being drawn down here. It's actually missing part of it, right? And the reason for that is because of the discrepancy in the rays. So our rays are shining out in 50 directions. There are not infinitely many of them, okay? So here you can see sometimes like the ray jumps from one side of a corner to the other side of a corner, like on the bottom. Like look down here on the bottom. You can see it sort of jumping like this. And so this, if I think I can just screenshot this, right? So let me screenshot. Then I'm going to bring it over here. So if we have this situation, what would the polygon that we end up drawing look like? Well, it will go from here to here. And you see that indeed it is missing this little part right here, right? So someone in the chat said, use more lines. But no matter how many lines we use, we're still going to have this problem. It's still going to look a little bit jagged. So, cleverly, we can think to ourselves, where does light actually stop? Right? Where does light actually stop? Well, it's going to stop at the corners. So what we can do is figure out all the vertices in this geometry and just shine line segments toward the vertices, right? You can see here that we have line segments going toward all vertices and then they're intersecting where they stop, right? So for example, the line right here is trying to get to this point over here, but it's intersecting before it can get there. So someone had the bright idea at one point to say, oh, look, just shine them at the vertices and then extend them until it hits the bounds of the walls. Okay. So what's happening here, if I can show you in a little bit more detail, is the following situation. All right. So we've got a polygon, oops, like this. Then we've got our light source up here like this, right? So what we want to do is we're going to shine rays outward at all of the vertices. Oh, we also have like walls out here. So I'm going to draw some walls. Okay. So we're going to draw this ray from here to here. However, it's going to intersect right here, right? So rather than, let's just say that red here, or that's not very colorblind friendly. So this one is going to that one, but it would intersect there. This one would intersect here. This one would intersect here, okay? However, we would want the shape to extend. If we've got another intersection over here like this, right? We can't just draw from here to here because the light would actually shine all the way back here. So what they do is for each vertex, instead of just drawing one line, they actually draw 3 lines. And the 3 lines are the actual line pointing straight at the vertex, and then they go left and right by like a fraction of a degree. So it's essentially the same line. However, the one that goes a fraction of a degree to the left will actually pass by that vertex and go all the way to the boundary, right? And the one that goes like a fraction of a degree to the right, well, it's going to hit the thing anyway, so it doesn't matter. So then we can draw these triangles. And this one will also have one to the corner because it's a vertex. And now we'll color, when we go to color, we'll color this thing in, and this thing in, and this thing in, and this thing in, right? So this is our light, and behind it we'll have the dark. And that's how we do it. So we go back over here. This is shining those 3 lines at every vertex. And then down here, now we're drawing all of the polygons. We radial sort in the same way, and we draw them all, and you can just see how smooth that is, right? Just absolutely deliciously smooth. So we solved that problem. And if we change it so that it looks like shadows, which is not actually shadows, there's no actual light going on in this environment, we're fooling it, right? So wherever the light is hitting, so up here we drew red for these polygons with a white background. Here, we have a black background with white polygons. And they've done some extra stuff where they have a few more lines on the edges so that they fan out and create this sort of blur-like effect, but it's just more lines, okay? It's not anything really fancy. And then what they do for the final effect is they just go through, and the background is an image, and you're drawing stuff from a different image on top of it. And this can be done with shaders really easily, but we're not going to get in depth about how we do that just yet because I have a whole lecture coming up on shaders, okay? But that's essentially it. That's all I wanted to cover today. So that's the last slide. I recommend going over to Sight and Light and looking at it, and that is 2D ray casting and line segment intersection, and it's what you need to know for assignment 4 and for your project. So if we go back real quick, in the next lecture, we'll be going over SFML cameras and views. We'll go a little bit of game design in this one and talk about why camera views can be interesting and they can help us with gameplay. And then we'll show some of the mathematics behind it and also how SFML is going to implement these cameras and views. If you were to do cameras and views in a 3D course, it would be far more complicated. Essentially, all we're dealing with in 2 dimensions is just rectangles and possibly rotations, but we're not even going to get that difficult or that into it. Cool. So good luck with assignment 2. It is due tomorrow. And please get started on assignment 3 as early as possible because that's going to be a lot of programming. So thanks a lot for tuning in, and I will see you in the next one.